Perfect. So let me just start by introducing myself. I'm Ayesha, the Director of ML Solutions and Architecture at Arctic AI. We're an AI consultancy based in North America. My role specifically is to oversee the development of custom ML solutions, and I am supported by a team of data scientists that help with through the implementation of ML pipelines all the way from scoping to deployment. I do have a background in software engineering and technology consulting. So let's just dive right into the presentation. Today, I'll be talking about the use of LLMs for security compliance assessment. All right, so we'll start off with the problem definition, followed by the technical solution architecture. I'll also walk you through how we've framed the experimentation and what the results look like, and what the future roadmap for this specific project was. This specific use case is actually a recent project we developed for a client who worked in the cybersecurity space. Um, the problem here at hand was in cybersecurity consulting, a lot of organizations need to bring the compliance of their IT systems, um, their internal policies and in compliance against standards, certain security standards like the NIST 853, which is based in US. In practice, this is done by the security consultants gathering information from clients, either through their internal documentation of the processes or through a security questionnaire, and then trying to identify the gaps where the organization's practices do not comply with the standards and the requirements within these standards. Now, these specific steps are pretty much time-consuming and very manual, and they're also very repetitive. So this is a good scope for automation. And then once these security consultants have identified these gaps, they use them to provide recommendations to the clients who can then act upon the recommendations and bring about any changes internally. Now, identifying automation here, not only reduces the turnaround time, it also helps organizations to act faster, and it also frees up the time of security officers to prioritize more critical tasks. I just wanted to give you an understanding of what these standards look like. So from a high level, this is a summary of the account management control within the NIST 853 standard. There are a few different topics here. You could see they're mainly associated with the management, monitoring, and auditing of accounts. And on the right, you'd see that there are certain standards need to be checked off, whereas others don't. There are 3 columns on the right here, and that basically is based on whether your organization falls under low impact, moderate impact, or high impact. It's also important to understand what these specific controls are and how they're structured. Right. So what I wanted to bring your attention to here is within a specific control family, you will have a set of baseline controls and a set of control enhancements. Baseline controls are the minimum requirement an organization needs to meet in order to comply with a standard, whereas enhancements are additional changes the organization can make to be more compliant. And the other thing that I wanted to highlight here is within each control requirement, we have what we call an organization-defined parameter. So these are essential entities that need to be extracted from the control standards and are useful for determining whether an organization is compliant or not. Examples of these are frequencies, time periods, job titles. So in this case here, you could see that the organization defined parameter is a retention requirement for auditing. And within the control enhancement, you could see another type of organization defined parameter, which is a frequency. So these are on different levels. Some are more direct standard data types like frequencies and time periods, but some are a bit more complex, like prerequisites, conditions for assigning and authorizing access to systems. And you'll see how we try to extract this and solve for this when we're developing the machine learning pipeline. But essentially, I wanted to bring your attention to what the language here looks like and how these controls are structured. This is a more concrete example. So this on the left, you see a response from a user to a question within the security questionnaire that the officers present to them. You could see how the user discusses what kind of systems allow group membership, what kind of controls they use, and in addition to that, what steps of authorization they need to go through to be able to gain access to the system. And then on the right, you see a control for AC2 within the NIST 853. And you see how different parts of the user response maps to different sub-requirements within these controls. It is essential when we're trying to automate this for us to be able to map which part of the security questionnaire is addressing these requirements and then determine compliance accordingly. There are a few key requirements that the client had set up for us before we started implementation. They wanted their users to interact with a conversational agent when filling out the security questionnaire, but they also wanted to be interactive such that the clients were able to bring their language in compliance while they're basically telling the conversational agent on how they implement their security practices. So this required us to build a low latency application, but there are a few other challenges that we were presented with when we're trying to implement this use case. The first was working with limited data. We did not have data access to historic records of security questionnaires nor internal documentations. Our only starting point was a single sample filled out questionnaire, and that was mainly due to privacy concerns around these questionnaires containing publicly PII data. The other complexity here, as with a lot of legal compliance use cases, is the convoluted language and the ambiguity, which leaves compliance open to interpretation. Well, as I walk you through the technical architecture, I'll walk you through how we address these challenges and fulfill these requirements. Now, the first step is to frame this problem as a machine learning pipeline. This was divided into two steps. The first being information retrieval, which was responsible for extracting key information from the user's responses, namely the organization-defined parameters. This included two types of information: standard entities like job titles, time periods, and frequency, and more complex prerequisites like conditions for access, and requirements for access. The second step in this pipeline is determining compliance against each requirement within the policy. For this, we needed to map each user response and the question to which controls they map to, as I identified in an earlier slide, but also identifying what the logic is to assess compliance. Now, that could be a set of logic-based rules, or they could be a bit more complex and an interpretation of the language used by the user. Now, compliance in this case was determined at the question level, such that we know which question to re-ask the user through the chatbot widget, as opposed to being at the policy level. And then policy level compliance was typically an aggregation and an AND operation applied to all the mapped questions. This is a really good example of using an LLM because we worked in a low data setting. We can leverage the pre-training and the language understanding capabilities the language model had adapted through the pre-training process. And any performance gain that we want to gain through, training the language model to be a bit more specific in this domain would be either done through prompting and fine-tuning the prompts or fine-tuning the language model. But since we had such limited data set, our experimentation mainly focused on prompt fine-tuning as opposed to fine-tuning the weights of a model. Our approach towards the solution was we build the automation in order to collect data, and through usage, we would be able to collect sufficient data that at a later stage, we can then fine tune the weights of a model. Can you go to the next slide, please? So how did we implement this, and what were the functional components of the solution? So as I mentioned, a key requirement was a conversational agent. This is in the conversational UI component, which is responsible for interfacing with the user via a chatbot widget. It also passes the user's responses to the middleware that then is able to process it through the machine learning pipeline. The middleware, in addition to passing data between the conversational agent and the ML pipeline, is also responsible for generating a summary of compliance reports that tell the security officers where the gaps are. And the security officers can then use this report to provide recommendations to their users. And then finally, the machine learning pipeline, as I mentioned, consists of two steps of information retrieval and then compliance classification, both which are powered by large language models. So if we could move to the next slide, this is what it looks like when those set of functional components are deployed on AWS. We are using Cognito as the identity service for authenticating the user into the chatbot widget, but also authenticating the different backend components, including the database, the email service, and the storage bucket with the middleware. The database here stores the conversation data as well as the machine learning outputs, since it is important to collect this information for future retraining. The storage bucket and email service are responsible for storing the generated report and then emailing the report back to the user or the security officer. The middleware is integrated with the LLM wrapper here and the NLU engine, which is implemented as Amazon Lex. And this is responsible for redirecting the conversation based on the machine learning outputs. Both the middleware and the LLM wrapper are deployed as a Lambda function, such that we can scale up those components based on usage. The LLM wrapper is then connected to an external LLM as a service. In this case, we use GPT 3.5, but this could be switched out with any other third-party service or internally hosted LLMs. So moving on to the next slide, there are a few key considerations that I wanted to discuss before we use LLMs in production. There is a bit of scaffolding that needs to be developed around the language model service before it's integrated into any backend application. So the first being prompt formatting and formulation. We need to be aware that we have the restriction of context windows when we're interacting with large language models. So when designing these prompts and formatting these prompts, we need to ensure that sufficient characters are reserved for the user responses. The prompt formatting block is also responsible for adding placeholders in the template with the user response, and again, ensuring that any context length is not exceeded. And as this formatted prompt is passed into the LLM service, it returns an output as unstructured text. So it is equally important to post-process the output and structure it in a format that is readable by the middleware. that is where this functionality comes from. This block is also responsible for any error handling in case the model silently fails. So in case when we're extracting entities of certain data types, those type checks are included in the post-processing block. Now, you notice that I haven't really specified technologies used because the space is changing and there are different modules that you can basically replace or within these blocks. So for output post-processing, a technology like prediction guard would be great, or function calling from OpenAI that was released not at the time when we were implementing this, but that could be essentially used here. In our case, we developed custom post-processing and within the solution. So moving on to the next slide. The other key considerations that you need to be able to look at are performance, latency, and cost. Since this is an interactive application via a chatbot interface, we wanted to ensure that we are able to generate the results with low latency, but we don't want equally don't want to call the language model multiple times. So through experimentation, we noticed that using a single prompt to extract all the organization-defined parameters within a single user response worked out better, both in terms of performance, but also in terms of how many calls you're making to the LLM service, rather than basically having separate individual calls for each entity or each defined parameter that you wanted to extract. So this also reduced the total number of tokens and, as an extension, the cost of using the LLM. And additionally, another thing that you want to be aware of are rate limits that are imposed by these services. So by grouping all the all the context the language model needs in a single prompt, it worked out better for this use case. The other consideration is making sure each component is modular. So as I mentioned, the pre-processing and the post-processing before integrating an LLM as service needs to be done in such a way that you're able to switch out the different components, including the service that you're integrating with. Next slide, please. All right, so I want to walk you through the experimentation framework. Our starting point was, as I mentioned, was a filled out security questionnaire and a PDF of the NIST 853, which had the policy requirements. Now, using this, we first of all replicated the security questionnaire in Amazon Lex and developed the dialogue conversation tree through this, basically, which was a replication of the questionnaire. But we also used the questionnaire to generate a data set using large language models, because what we had was not sufficient for evaluation or any kind of prompt fine-tuning. So the way we did this is we used GPT 3.5 to generate 100 conversation sessions that replicate the conversation design that we have in Lex, and then went through a quality assurance process to finally create a ground truth data set that we'll use during experimentation. Additionally, we cross-referenced the security questionnaire with the NIST standards to map questions to the data points that need to be extracted, but also map questions to the policies and identifying what logic is required to check for compliance. Using this information, we designed a few initial prompts and passed those prompts through the model. Basically, we assessed them through quantitative metrics, but also another set of QA where we involve domain experts to identify the performance of these prompts. And that was an iterative process. So any feedback from those two would go back into prompt design. We'd version control the prompts and then repeat that experimentation. As I mentioned, we did not have enough data at this point for any model fine-tuning, so most of the experimentation focused on prompt fine-tuning. All right, next slide, please. Now, I think for evaluation, it's important to understand what a correct extraction is. And as I mentioned, certain types of organization-defined parameters require stricter checks than others. So there are two levels to this as well. One is being an exact match, where the entities needs to be extracted entities from the model needs to be an exact match of the predictions and the ground truth. So in this case, we use certain classification metrics, and before running them through those metrics, we pre-process them by removing any capitalizations and lemmatizing both the ground truth and the predictions to their root word. Now, the other type, which are more complex data points, such as prerequisites, conditions, or reasonings, is where the model's output is likely to vary from the ground truth even more, either because the model has generated a paraphrase of what the ground truth is, or the model has fewer or more words than the ground truth. Neither of these cases mean that the model's prediction is incorrect, but so that hence exact match does not really suffice here. And what we want to be looking at is evaluating the model's prediction on a semantic level. So moving on to the next slide, so these are the basic metrics that we've used to evaluate performance on a quantitative level. Precision, which basically is how many of the entities extracted by the LLM were correct, and then recall how many of the entities present in the ground truth were identified by the LLM. F1 score is what we focused on here, which is basically a balance between those two metrics. Because we wanted to balance out between the false positives and the false negatives for this specific use case. And then finally, for information retrieval, we used cosine similarity, which means we're looking at the model's response from a semantic level. In this case, we leveraged BERT to compute the embeddings and then ran them through a cosine similarity function to compute how similar the ground truth was to the model's predictions. So next slide. So now we've identified the metrics. We also had a bit of optionality around what kind of language model we wanted to use. The client did not want to invest a lot in experimentation, and this was the initial investment that they were making in this use case. So we had to quickly turn around, we had to have minimal technical investment into this solution as well. But essentially our optionality here were open source or LLM as a service. Now, when it came to open source, a lot of the language models are pre-trained on generic data sets, but they tend to perform well on much more limited number of topics, whereas with LLM as a service, they typically are trained on larger volumes and then are more generalizable. The next bit was looking at the performance and fine-tuning capabilities. You have more control over fine-tuning the model weights on your domain-specific use case data set, but it requires considerable training data, which is what we did not have. Whereas in LLM as a service, there is less control provided to the user, especially with a lot of these proprietary models. And so some of which do offer fine-tuning capabilities, some of which don't. Hosting is also a big key consideration. Open source models require to be hosted on internal infrastructure. There is tooling around hosting that is available, such as Amazon Bedrock providing integrations with a lot of these open source models. But you have to consider the cost of infrastructure. The latency is also dependent on what kind of compute and memory resources you select. Whereas an LLM as a service, they are already taking care of hosting it within their infrastructure, which is already optimized for low latency. Dependency on third parties is another consideration. So when you are internally hosting an open source solution, open source LLM, there are no or minimal external dependencies, but because you are doing most of the maintenance internally, but provider of an API can choose to stop the service at any time. And so your availability of your solution is dependent on the availability of the LLM as a service. Next slide. The last and the most important factor here, given that this is in the cybersecurity domain, is data residency and privacy. In open source, since you are hosting it internally, you can control the data flow, and it likely lives and stays within your own environment. Whereas when you're using public APIs, your data does get passed on to the service. And so you could leverage certain techniques like anonymizing your data before you pass it to the LLM, but there is a risk of data leaking into the service and that the service using it for their own purposes. So these are a few factors that you need to consider between the two. Now, because we had limited data, as I mentioned, we started off using LLM as a service, keeping in mind that we would eventually want to create our own verticalized LLM solution and host it internally. So moving to the next slide. So now that we've started experimentation, we've chosen a couple of LLM as a service providers that we want to test out with. We wanted to understand what's the best way to structure the prompt in order to be able to extract the information that we need. We observed that there are three key factors here that need to be provided in the context. So the first being description of each variable that needs to be extracted along with the variable name and what type of format it is. So for example here, we want to extract the types of systems that permit group access. We've defined what that variable systems permit group access group membership means, but we've also defined that it's supposed to be extracted as a Python list. And then we have a placeholder for the user response where we're going to extract this information from. This is what we noticed worked best across the board. We did experiment with a few other formats, but this is what we ended up with. Next slide, please. All right, so that was for the information retrieval use case. Now looking at the compliance classification, which is a bit more involved. As I mentioned, that we mapped each policy to the question number. So what we are configuring for each question is what kind of rules do you want to check against the entities that we've extracted in the previous step. So you could see that there are a list of rules like non-empty, equal, less than, greater than, and then there is a optional placeholder for a prompt if we wanted to bypass the assessment to an LLM. The reason why we have rules here and we haven't just used an LLM prompt is because we want to minimize the calls to the LLM as much as possible. And if we're able to do that through a set of standard rules, that's great. Both these prompts and these configurations are actually stored in the database, and then they're passed to the LLM wrapper via the middleware. So when we do run experimentation and notice that we need to update a prompt, or even through monitoring of the solution, we notice that the model is performing, or this ML pipeline is not performing as well on a specific compliance policy, then we will only need to configure that in the database. and update the database without changing any other part of the solution. All right, so moving on to the next slide. So this is what a sample output looks like. Again, on the left, you have a user response, and on the right, you have what has been extracted by the LLM and the format that you needed. So here we specified that we want it as a Python list of strings. That is how we got the format, and then this is going to be parsed by the middleware. All right, moving on. So just summary of the results and what the future roadmap looks like. So we specifically tested against GPT 3.5 and AI 2.1's Grand Instruct model. We noticed that GPT 3.5 was more robust in comparison. It performed better in a zero-shot setting, whereas AI 2.1's model performed better in a few-shot setting. It required a lot more examples to be engineered into the prompts. And since we had to work with limited data, the former option was more preferable. Responses generated from the instruct model also were had a few shortcomings. So they were likely to contain the question prompts that we passed in the context, but they also had a higher likelihood of extracting irrelevant parts from the user response. And they were also sensitive to the formatting changes. So if there was any changes in the spacing, regardless of what the content was, then the outputs would differ. So they weren't very repeatable. And so for those reasons, we used GPT 3.5 as our model. It also proved to be more cost effective because the prompts were shorter. All right, so quick summary of the results. In entities such as job titles, account types, systems were easier to extract. Process-related variables, access requirements were a bit more challenging for the model because this is where the model was likely to get a bit more creative, but it still performed well for our purposes. Compliance classification, we noticed that it performed well when the policies were mapped to a limited set of questions as opposed to, and ones that had rules-based checks as opposed to ones that were mapped to several questions or had a combination of rules and prompt-based checks. The next slides have a quick summary of what that looked like for each policy, and it highlights which policies need to be improved. So I'm just quickly going to gloss over the next two slides. And then the final slide is on the roadmap. So for this current case study, it was a feasibility study, and our main focus was data collection through the usage. So we mainly focused on prompt fine-tuning, but our roadmap for this specific client is to collect sufficient data and then fine-tune either an open source model or an LLM, proprietary LLM offered as a service for performance improvement in the domain. Eventually, we do want to self-host a verticalized LLM where on an internal infrastructure, but that comes with, as we are moving away from LLM as a service, we do need to focus on, safeguarding our model a bit more through, threats such as prompt injection, content moderation, all of which were offered as part of LLM as a service behind the scenes. So that's some components that we would need to develop. And yeah, that's a quick summary of what the next steps look like. I'm going to take any questions